rate you will demand, because it would be hard for you to resell the bond you bought, for example, the instrument you bought, because when you'll have a sudden need of money. So here, the fourth compensation is called the liquidity risk premium. A last compensation is linked to the sensitivity of the instrument you bought. What do we mean by sensitivity? The sensitivity is the risk, if you want, of variation of the price of the instrument you bought when the interest rates in the market change. We will see this with different details when later in the fifth chapter. We will explain it better. Here in this introductory chapter, I just want to say that the interest rate of that we use has different components, and there is no difference. We will not distinguish between the interest rate and the inflation, because many students have the idea that the value of money may vary because inflation. It's not because inflation only, it's because interest rate. In the interest rate, inside the interest rate, we have the inflation, we have the default risk, we have the liquidity risk premium, we have the maturity risk premium, in addition to the real interest rate. We call it the real risk free. We will come back, we will see more details concerning the components of the interest rate in the fifth chapter. Now, to be able to solve the time value problems, we need to visualize what is happening in a particular problem to be able to set up the solution for the problem. To visualize the problem, we need to make a graphical representation of the different cash flows and their timing. When we say cash flow, we mean by cash flow an amount of money that we will invest or that we will receive. We call it cash flow. The cash flow could be an outflow of money or an inflow of money. Here we will not focus on the sign of the cash flow. We will say a cash flow, an amount deposited at a particular date or received at a particular date. We call it a cash flow. In the timeline, we have different tick marks here. Each tick mark represents the timing of the cash flow. For example, the date 0 represents today in general. And the date 0 represents the beginning of the first year or the first period. The end of the first period, 1 represents the end of the first period. So each number here represents the end of the year. So 1 represents the end of year 1 or period 1, which is also the beginning of period 2. 2 is the end of period 2, which is also the beginning of period 3. It's very important to respect this logic of representation of the timing of the cash flows to be able to compute the correct present value or future value later. For example, we can have a lump sum, a $100 lump sum due in 2 years. A lump sum means a single amount that we will pay or that we will receive after 2 years from now. This is today, the date 0. This is 1 year from now. This 2 years from now. 2 years from now, we will pay or we will receive $100. For example, we can have a 3-year $100. When we have the same amount received or paid equidistant intervals during many years or many periods. we have the same amount, 100, 100, 100. In this example, deposited or received at the end of each year or end of each year. We call it an annuity. And since the deposit or the amount is received at the end of year 1, end of year 2, end of year 3, the first amount occurs 1 year from now, we call it an ordinary annuity. We have also an annuity due. We will see the difference between the two later. Or we can have an uneven cash flow stream, a mixed stream if you want, a series of unequal cash flows reflecting no particular pattern. For example, we decide to invest 50% in an investment account, deposit $50 or $50,000 today, 70 1 year from now, 10 2 years from now, 60 3 years from now. This is an uneven cash flow. Now, to compute the present value and the future value, we apply different processes. The present value represents the value today. When we compute the present value, generally we mean the value today in current dollars of a sum of money to be received at a future point of time. So we have a future value or a future cash flow that we receive, for example, at the date N. And we need to compute its value today at the date 0. So we pass from the future to the present. The process that will allow us to move back in time to compute the value today of an amount to be received in the future is called in finance the discounting process. It's the process that we use to calculate the present value of a future cash flow. The reverse of the discounting is called the compounding, which allows us to compute the value of a given sum of money today measured at a specific future date. So we pass from the present to the future. And the compounding process consists on moving cash flows forward in time. And this is the process of going from today's value, the present value, to a future value. To be able to compute the present value or the future value, as we said, we need the interest rate. And this interest rate will constitute for us the discount rate that we will use to pass from the future to the present. The compound interest rate, if you want, what we will use to pass from the present to the future. Now, to compute the future value or the present value, we have different principles of interest. We can either use the simple interest process or the principle, or the compound interest principle. In all the finance courses that we will see, we use the compound interest principle. But we need to understand the difference between the two. When we use the simple interest principle, the interest that we compute is computed on the basis of the original amount only. Suppose we have $100 today. These $100 will constitute the basis on which we will compute the future interest for all the future periods. So the interest is computed on the basis of the original amount of the principal only. This is called the simple interest principle. So, for example, if you earn interest during the first year, this interest will not generate another interest. No, the interest of the second period will be computed on the original amount only. For example, assume that you deposit $100 in an account that earns 10% simple interest for 2 years. What is the accumulated amount at the end of the year 1? And what is the accumulated amount at the end of year 2? When we apply the simple interest principle, the 10%, the interest is computed on the basis of the $100 each year. So each year we will have the same interest. For example, here at the end of year 1 or the period 1, you will have your original amount deposited plus the interest on this original amount, 10% times 100, we will get $10. So the obtained amount, future value at the date 1, is simply the present value at the date 0 plus the present value times the interest rate. So it will be 100 times 1 plus the interest rate, $110. Now, at the end of the second period, the second year, the interest is not computed on the basis of these 110 on the accumulated amount. No, here the interest is computed on the basis of the original amount only, because we are applying the simple interest technique. So during the second year, we will find in our account the original amount, 100, the interest earned during the period 1, the first year, and the interest earned during the period 2, which is calculated on the basis, as we said, of the original amount, 100. Another 10, you will get 120. So the future value at the date 2, end of year 2, will be 100 plus 10% times 100 plus another 10% times 100, which gives us 100 times 1 plus 2 times the interest rate. So when we apply the simple interest technique, the future value at a particular date n, or an amount invested today at the date 0, is equal to the present value of the date 0 times 1 plus n times the interest rate. N represents here the number of periods of interest, number of time periods from the date 0 to the date n. From 0 to n, we have n minus 0 years or periods. The general formula, suppose that the present value is not invested today at the date 0. Suppose that we invest the 100 at the date, for example, 6 or 7 or 3. So at the date t, and the formula, the number of periods of interest is the difference between n and t. For example, if you invest your money at the date 1 and you want to compute its value at the date 6, the number of periods of interest from 1 to 6, you have 6 minus 1 years, 5 years of interest. So we will put the number of periods of interest here between parentheses multiplied by I. It will be n minus t, the number times the interest rate. For example, if here we are asked to calculate the future value 5 years from now, 5 years from now is the date 0, 5 years from now is the date 5, of $300 deposited at the end of the second year. This is today, this is the end of year 1, this is the end of year 2. At the end of the second year, we will deposit 300. These 300 will generate 6% simple interest. What would be the obtained amount 5 years from now? It would be 300 times 1 plus the number of years of interest from 2 to 5 is 5 minus 2 years, 3 years, times 6%. You will get $354. Now, if we use the compound interest process instead of the simple interest process. Be careful, do not confuse compounding process with compound interest. Compounding process consists on computing the future value. The compound interest is the technique we will use, the principle we will use. When we use the simple interest, as I said, we compute the interest on the basis of the original amount only. But if we use the compound interest principle, we compute the interest on the original amount invested as well as any previous interest earned. For example, if we invest $100 today in an account that pays 10% compound interest for 2 years, 1 year from now, the amount invested is 100. This 100, we will compute the interest on the basis of all the amount available in the account. The amount available on the account at the beginning of the year is 100. So we will earn 10% on the 100, we will get 110. It is similar to the simple interest principle. But from the period 2, from the year 2, we will have a difference here. When we use the compound interest, we said that we earn the interest on any accumulated amount, not only on the original amount. So in our account, since we have 100, we will find the $100 original amount. The 10% on the original amount, which represents the interest of the period 1. Now the interest of the second year is computed on not only on the original amount 100, on the original amount as well as on the previous interest earned. So we will have 10% on the original amount, that represents another $10, and the additional interest, if you want, compared to the simple interest technique, is the interest on the previous interest, the interest on the $10 earned during the year, which will give us an additional $1. So the interest of the second period here is not $10 only, like in the simple interest principle, is 10 plus 1 is $11. And here, the difference between the simple interest and the compound interest in the from the second period is the interest earned during the second year on the interest earned on the previous year, in the first year. So earning interest on interest, and our the compounding interest. Compounding the interest means earning interest on the previous interest. So here, since the calculation will take this form, 100 times 1 plus 10%, and we will find this in the second period, 100 times 1 plus 10%, as well as 10% times all the obtained amount, which will give us $100 times 1 plus 10% squared, power 2, not 1 plus 2 times 10%, in the simple interest process or principle. We have here 121. So the general formula will be, if we invest an amount PV0 today at an interest rate I for n years, n periods, the future value n will be the present value 0 times 1 plus I, power the number of time periods from 0 to n. From 0 to n, we have n minus 0 periods. So it will be power n. And more general formula, when you invest an amount at the date t, its future value at the date n will be present value times 1 plus I power n minus t. So the first formula is particular, if you want, case of the second one, when here t is 0. For example, suppose that we are asked to compute the future value of an initial $100 after 3 years if the interest rate is 10%. Here, the future value at the date 3 is equal to the present value at the date 0 times 1 plus I power 3 minus 0 power 3. We have $133.1, the obtained amount at the date end of date 3, end of year 3. How to decompose, if you want, this these $33.1 of interest. The $33.1 of interest, you find them here. If we invest $100 today, 1 year from now, these 100 will generate $10 of interest. You will obtain 110. End of year 2, the original amount will generate 10. The interest of year 1 will generate $1. You will get 100 plus 10 plus 10 plus 1, 121. End of year 3, you will find in your account your initial amount, the interest 1, interest 2, as well as 10% of the original amount, 10% of the interest 1, 10% on the interest 2. You will get $133.1. So these are the principles of computing the future value when you use the compound interest technique. If the investment is not made today, if the investment is made at the date T, here investing, for example, $300 at the date 2 years from now, knowing that these 300 will generate annually 6% compound interest, the future value at the date 5 will be present value at the date 2 times 1 plus 6% the interest power the number of years of interest. From 2 to 5 we have 1 year, 2 years, 3 years, 5 months, 2 years, power 3. You'll find 357.3. Of course, the future value, everything held constant, the interest, the number of periods, and the amount invested. Applying the compound interest will generate more interest than applying the simple interest because of the compounding process, because of the interest on interest. Now, in the real life, the simple interest is used when you invest your money on the short run or a period lower than 1 year. In this case, the interest is computed on the basis of the number of days of deposit, for example. And the compound interest is used when you use, for example, an investment that generates interest on interest, even if the investment is for a period lower than 1 year. When the interest is compounded, for example, monthly or compounded daily, we will see this later, the interest earned during the first month will generate another interest during the second month, etc. Okay, but as I said, in the remaining of our chapter, we will only use the compound interest principle. We will not use the simple interest anymore. I just introduced it to understand the difference between the two. Now, as we used the compounding process, I'm not talking about compound interest, compounding process going from the present to the future, computing the future value of a present investment deposit. We can do the reverse. We can compute the value today of an amount to be received in the future. Or we want to determine the value today of something that we will pay in the future. Here we will use the discounting process, the reverse of the compounding process. Here, since the future value at the date n is equal to the present value of the date 0 times 1 plus I power n, here the present value at the date 0 will be the future value of the date n divided by the interest factor 1 plus I power n. We call it in finance interest factor 1 plus I power n. We divide the future value by 1 plus I power n. Here in this case, I is called the discount rate because we are discounting the future value to compute its present value today. The discounting process consists on eliminating the interest from the future amount. This is why in the formula we can put future value times 1 plus I power minus n. The negative power here, when future value, an amount is multiplied by 1 plus I power minus the number of periods of discounting, the minus reflects the fact that we have to subtract, to eliminate the interest from the amount, to reduce the amount. Because when we go forward in time, from the present to the future, the value will increase, the obtained amount will increase because we add interest. The power is positive, the n is positive. But when we go back from the future to the present, we have to eliminate the interest. We divide by 1 plus I power n, or we multiply by 1 plus I power minus n. When we want to compute the present value at a date which is not 0, it's not today, at the future date, going from the date n to the date t, consists on subtracting from the future value the interest of n minus t years. So we divide the future value by 1 plus I power n minus t, or we multiply the future value by 1 plus I power minus, between parentheses, the number of years of discounting or the number of years of compounding. For example, here, suppose that we need to determine the value today, the present value of $100 due in 3 years. If the interest rate is 10%, for example, suppose that you have to reimburse your colleague $100, for example, 3 years from now. What is the value today of these $100 in the today's dollars? We have simply to divide the 100 by 1 plus I power the number of years of discounting from 3 to 0. We have 1 year, 2 years, 2 years, 3 years, power 3. Or we multiply the future value by 1 plus 10% power minus 3 to say that we are eliminating the interest, these 10%. So the value today of $100 to be paid or to be received 1 year, 3 years from now is 75.15. Now, what is the meaning of these $75.13? Suppose, for example, that you have to pay to your colleague $100 3 years from now. But he said to you that he prefers that you reimburse him today. You will not reimburse him today $100. Why? Because simply, if you keep the 100, you do not reimburse the 100 today, you can earn 10% annually on these 100. So if you invest 100 today at 10%, the obtained amount will not be 100, will be higher than 100. We said it will be $133.1. It's not 100. So if You decide to reimburse the money today, not 3 years from now. You will pay to your friend only 75.13, because 75.13, if he get the money today, 75.13, he can invest the 75.13 at 10% during 3 years. He will get the $100. In this case, the 10% is called an opportunity cost. An opportunity cost, because if you do not wait until 3 years to pay your friend, you will lose these 10%. You would have earned only 10% if you kept the money. If you reimburse the money to them. So this is why I said that understanding and mastering the mathematics of time value of money will change the way you think about many things. So if you will receive, or for example, you will not pay 100, suppose that you expect to receive $100 3 years from now. What is the amount that will make you indifferent between receiving $100 3 years from now or an amount today? The amount today that replaces the 100 that you will receive 3 years from now is 75.13. As I said, because 75.13 today invested at 10%, which is the interest rate available in the market, will allow you to get the 100 3 years from now. So the interest rate, 10%, is at the same time a discount rate that we use to compute the value today of an amount to be received in the future, a return that you can obtain if you invest your money today during an period, or an opportunity cost for you when you, if you want, that reflects the fact that you could have invested your money in a particular project or something else that would generate it for you 10%, for example, annually. Do you have questions concerning this part, please?
اي مسيو بلي نحب نسال على وقت اللي حكينا كيف نعملوا الانفستمنت في التي مش باش نعملوها توداي الانفستمنت تاعنا جوست جو فودري كومبروندر علاش ناخذوا التو دانتيغي اللي هو توداي اسكو ما يتبدلش معناها علاش ما ناخذوش
احنا in our calculation we suppose that the interest rate is constant.
Okay.
We suppose that the interest rate is constant, but suppose that the interest rate would change each year. For example, let's say take this example. Let's take this example. If you invest 100, for example, today for 3 years, or at any date, today for 3 years, if the interest rate is 10% during the first year, 10% second year, 10% third year, we can apply this formula. But suppose that the interest rate during the second year is 12%. The third year, the interest rate is 9%. The future value, we can't compute it like this. We will compute the future value 1 separately, then the future value 2, then the future value 3. The future value 1 will be 100 times 1 plus 10% power 1. Then these 100 times 1 plus 10% power 1 will generate 12% interest during the second year. So you multiply 100 times 1 plus 10% by 1 plus 12% power another year of interest. Then 100 times 1 plus 10% times 1 plus 12% multiplied by 1 plus 9% the interest rate of the third year. So we compute the future value at the end of each year separately. We can't determine directly future value 3 like this, because the interest rate is not constant. Okay? The same thing here, if you invest your money at a future point of time at the date t. Here we are supposing that I is constant until the date n. But if the I is not constant until the date n, we have to compute future value at the date t plus 1, t plus 2, until the date n each year separately. Is it clear?
Yes, thank you.
Yes.
بعد هذا نشوفوا simple interest formula.
Now the simple interest سيدي. We will not cover it anymore. عندنا different other واحد calculations that we can use when we consider the simple interest. But as I said, we will not use it simple interest. For real life in general, we use the compound interest. Okay.
شو معناتها في أي exercise ولا في example معناتها ما نحتاجوش باش يسمينا
with default use the compound interest. If I demand to use the simple interest, I will say it. I will mention it. Using the simple interest, compute the future value. But if I say the interest rate is 7%, I suppose that the interest rate by default is a compound interest. Okay?
Okay, Mr.
Mr. Blay, I have a second question. At the beginning of the session, the question اللي حطيناه هو est-ce que معناه you accept to take the amount today وإلا تحب تاخذه بعد. Just لهنا نحب est-ce que الكويستيون هذيا in case أنه total amount will be invested أكهو معناها الشواء متاع أنك تاخذه اليوم وإلا تاخذه في معناها عام آخر ولا اللي هو in case أنه total amount اللي باش تاخذه today الكله باش يمشي investissement. ما نحكيوش على consumption ما نحكيوش على حتى شيء.
Even if you decide to consume it in general according to based on the even on the inflation. In general the inflation is positive, it's not negative. حتى if you want to consume وكهو we will not invest. The price that you can buy today for something in general is lower than the price 1 year from now in general. But in finance, let's call it the logic about the way of thinking about many things will change. In finance ما عنديش أنا money مخبيها تحت المخدة نتاعي. لا in finance ما عندي opportunity cost. فما حاجة اسمها opportunity cost. أي amount that I have I need to maximize the profit اللي باش يجيني منه. تقول لي $100 today $100 1 year from now. إذا كان ال $100 خديتها today ما عملت بيها حتى شيء 1 year from now the value of the 100 will not be 100.
أقل.
مش تكون أقل. Okay?
Yes. Thank you so much.
مش سألتك كيستيون هيك موجودة في الكومنت سيكشن.
بالله يقول لي خاطر راني ما نجمش نقعد
سامحني.
يقول لي ميساج
مسيو الانترست ريت اللي نحكيو عليها مسيو هي نفس الانترست ريت اللي شفناها في ديبيو شابيتر اللي فيها all the compensations معناها LRP وكلها.
Yes, هذيك تعطينا an idea about the determinant of the interest rate. And we will not focus on the component now. We will say that we will try to learn the mathematics of how to compute the future, the present. We will have a whole chapter concerning the component of the interest. We'll compute the interest. This is the risk-free. This is the inflation premium. This is the rating of the company. This is the maturity risk premium. Compute I if you decide to invest your money for 3 years, I for 10 years, I for 20 years. هذيك حكاية أخرى that we will cover in a future chapter. Here we consider that the interest is given, or we need to compute it according to the present value, the future value. not according to the component of the interest rate. Is it clear?
Yes sir, thank you.
نجم نقدموا؟ Yes.
مش عندي كيستيون. ديما لازمنا نحسبوهم معناتها بالطريقة هذه ولا نجم we can use التيبلز اللي فيهم لي تو كل.
التيبلز اللي فيهم الانترست ريت فاكتور والانترست فاكتور annuity is not always available تحت يدك. or even في exam. or even
ما تعطيوهم لناش في الاكزام.
ما لناش نستحقوا ياسر قد كما قلت لك. It's not always available الحاجة هذيك. دونك أنا ماذا بيا عندك calculator basic calculator you can compute the future value the present value. Okay. You don't need documents to be able to compute the future value of the present. Okay?
Okay.
Okay. Suppose now that we need to determine the number of periods, not the future value or the present value, that will allow us to accumulate an amount, knowing the interest rate earned to be earned each period, and the initial investment earned. For example, if we invest today $20,000 at the annual compound interest rate of 9%, after how long the future value would be equal to 36,560. So in this case, we need to determine the n. Since the n here is in the power, future value n equal present value 0 times 1 plus I power n. To determine the n, we need to eliminate this power. To eliminate this power, we need to use the logarithm. So logarithm of future value n must equal to the logarithm of present value times 1 plus I power n. Logarithm a times b is equal to logarithm a plus logarithm b. Logarithm b power n is equal to n logarithm b. So here n, we can compute it. So n is simply equal to logarithm future value minus logarithm present value over logarithm 1 plus I, or simply from the beginning we can say 1 plus I power n is equal future value n over present value 0. It will be here in the denominator logarithm between parentheses future value n over present value 0, or logarithm future value minus logarithm present value over the logarithm of 1 plus I. This will allow us to estimate the number of years required to pass from a known present value to a known future value using a known interest rate. So here the unknown parameter is the number of periods. Is it clear here?
بس ديما نعملوا arrondissement up.
What?
C'est l'arrondissement qui يجي
just only basic examples simply to understand how to determine the unknown parameter. Okay, calculation بعد ديما arrondissement بعد two figures بعد الكلام. Now suppose that we know the present value, we know the interest value, the future value, we know the number of periods of investment, and we need to determine the interest rates used. Always we will use the same formula, future value n equal present value 0 times 1 plus I power n. If we invest, you invested $5,000. And after 6 years, the amount of money accumulated is 9,352. At what annual compound interest rate I, the investment was made? Simply future value n is equal to the present value 0 times 1 plus I power n. We need to determine the n, the I, but to determine the I, we need to eliminate the n. Not like in this example, to eliminate the n, we have two choices, two alternatives. we can use, we'll put both sides of the equality power 1 over n to get power n, and power 1 over n will give you power 1, or we can use the nth root. Yeah, you will have the same thing. For example, if we take this power n and this power n, we can eliminate a 1 over n. 1 over n. We can eliminate this n, it will be power 1. Present future value n over present value 0, power 1 over n. So we simply subtract this one. I is equal to the future value n over present value 0, power 1 over n, or the nth root of the future value over present value. Don't forget the -1 to get the interest rate. Here the interest rate is approximately 11%. It's very simple. Huh? Now, according to this principle of time value of money, I said $1 today is different from $1 that we will receive or that we will pay in the future. So here we can't make the sum of $2, two cash flows that will occur at different dates. This is known as the cash flow additivity principle. According to the cash additivity principle, we cannot add or subtract cash flows that occur at different times without first computing their value by compounding them or discounting them to the same point in time. So, for example, if you have $100 today and $100 1 year from now, we can't say that their value is 200. No, we have to compute the present value of the 100 that we will receive 1 year from now. Its present value today. Then we can add it with the 100 that we have today. Or we can compound the 100 that we have today to compute its value 1 year from now. Then we add it with the to the 100 that we will receive 1 year from now. Okay, so if 2 or more cash flows occur at the same point in time, we can add or subtract them together. But if the cash flows occur at different timings, we cannot add them or subtract them. Let's take an example to better understand this, to understand or how to solve for unknown values if we have different cash flows that occur at different times. Suppose you have decided to start your own firm. Being prudent, you want to have enough money, save it to use for living expenses for 2 years before you quit. You can currently put away $45,000 a year. You can save at the end of each year $45,000. And you know that you will have living expenses of $75,000 a year for each of the 2 years. So to simplify things, we will suppose that at the end of the 2 years during which we will consume, etc., we have to pay at the end of each year $75,000. These are the expenses. You would like to quit in 3 years. So you will make 3 savings. If you put $45,000, the savings of year 1, and the savings of year 2, $45,000. At the an interest rate equal to 5%. If you deposit this in an account that will pay you 5% annually, how much must you put in the account at the end of year 3 so that you can quit? How to convert this problem into a timeline or a financial equation, if you want. Here, if we save 45,000 at the date 1 and we save 45,000 at the date 2, we put both in a savings account. We need to put a third amount at the end of year 3. The obtained amounts, the accumulated amounts at the date 3 must allow you to cover $75,000 expenses that you will pay at the end of year 4, and another $75,000 that you have to pay at the end of year 5. So to be able to quit, what you will save during these 3 years must cover what you will invest, well, the expenses of these 2 years. If we didn't check this course of finance or time value of money, some students can simply make 45 plus 45 plus x must equal 75 plus 75. Here we ignored the time value of money. But since we understood the time value of money and this logic of that we can't add dollars that occur at different timings without computing their present value or their future value at the same time, we can make the sum, or we can subtract one amount from another. But here it's not correct to add dollars with the 2 amounts or different amounts that occur at different timings without computing their value at the same date. So we're here to be able to make the sum of these 3 and we subtract these 2 to get 0. So to say that the sum of what we accumulate, what we will obtain is equal to the sum of what we will pay. We first need to compute the value of all what we will receive and all what we will pay at the same date. In general, the date is the current date today. So in general, we compute the present value of 45 that we will save until the date 1. The present value of the 45 that we will save at the date 2. The present value of what we will save at the date 3. And the present value of what we will pay at the date 4. The present value of what we will pay at the date 5. This is one way of solving this problem. Another way consists on computing their future value, but in general, the logic is to compute the value today of what we will receive and what we will pay in the future, to make things simpler. So applying the first logic, what will be the present value of 45, date 1, 45 to accumulate at date 2, 45 to say the future value 3 at the date 3, minus 75, it means that we have 75 to pay at the date 4 and another 75 to pay at the date 5. Applying the time value of money, 45,000 to receive 1 year from now, or to save 1 year from now, its value today is 45,000 over 1 plus I power 1, because from 1 to 0 we have 1 year of discounting and the discount rate is 5%. 45,000 to save at the date 2, its value today is 45 over 1 plus I power 2. The present value of an amount that we will save in the future, we call it here future value 3. Its value today is future value 3 over 1 plus 5% power 3. Then we add cash flow 4 and cash flow 5 also. Cash flow 4 and 5 are negative since these represent expenses for us. So present value of minus 75 today is equal to 75 over 1 plus 5 power 4. We put minus here to say that these will represent expenses. The last 75,000, we will pay them at the end of year 5. It's present value. The present value of this amount, 1 plus, we divide it by 1 plus 5% power 5. The sum of all these amounts must be 0 to be able to quit. So here, to compute future value 3, we simply take the 75 and these minus 75 on the other side of the equation. They will become positive. And the 45, the other side of the equation will become negative. Then, to eliminate over 1 minus 1 plus 5% power 3, we multiply the obtained amount by 1 plus 5% power 3. You will get future value 3, $42,593.28. Another way of computing this unknown amount is to, since the unknown amount will occur at the date 3, to compute its value directly at the date 3, simply we will compute the value of 45 minus 75 at the date 3, not at the date 0, to avoid discounting even the future value 3 to the date 0, to save time. So simply, instead of computing the present value of all these positive and negative amounts at the date 0, we will compute their value at the date of the amount that we need to compute, that we need to determine. So here in this case, since the date 3 represents a future date for an amount that we will save at the date 1 and the date 2, and it represents a present date, of a present value for the date 4 and the date 5, for the minus 75, minus 75. It means that in our equality now, we will compound 45 and 45 until the date 3, and we will discount the 75 and the 75 from the date 4, the date 5 to the date 3. This mathematically will give us this equation. The present value 3, the future value 3, only the future value 3, this amount, x, the unknown amount, is equal to this compounded plus this compounded minus this compounded discounted minus this discounted. So to compound 45 from 1 to 3, from the year 1 to the year 3, we will compound it for 1 and 2 years. So this 45 at the date 3 will give us 45 times 1 plus I power 3 minus 1, n minus t. 3 minus 1, 2 years. The second 45 from the date 2 to the date 3 will become 45 times 1 plus 5% power 3 minus 2, 1 year, 1 additional year of compounding, power 1. Then these minus 75,000 discounted from 43, from the year 4 to the year 3, we have 1 year of discounting. So it will be power minus 4 minus 3, which is power minus 1, or we divide it by power 1. The same thing from 5 to 3, we discount the 75,000 for 2 years, we divide it by 1 plus 5% power 2, or we multiply it by 1 plus 5% power minus 2. This will give you directly the same amount that we need to save during the date. And to be able to compute, well, to make the sum or to subtract different amounts occurring at different dates, it is important to compute their value at the same date. This same date could be the date 0, could be the date 3, it can even be the date 5 or date 1, date 2, any date you want. But there is a logic behind this. Simply, in general, we use the current date or the date of the unknown amount. I hope it is clear. Do you have questions? Do you have questions?
Monsieur, إذا كان we choose ال T5 الكومباوند اوت الأولانية اللي هي على بيسونس 2 بيسك هو معناها he will quite في بعد عامين دونك تقعد على بيسونس 2 ما توليش على بيسونس 1 2 3.
If you choose the date 5, you will move all the amounts to the date 5. It will be 45,000 times 1 plus 5% power 1 2 3 4 plus 45,000 times 1 plus I power 1 2 3 plus the unknown amount future value 3 times 1 plus 5% power 1 2 minus 75 power times 1 plus 5% power 1. We will compound this to the date 5 power 1 plus minus 75,000 without any compounding or discounting, and you compute the future value 3.
Yes.
Okay.
Yes.
Is it clear for everyone?
Yes.
Let's just finish this part 2 to be able to do some exercises in the tutorial. So now, suppose now that we are we want to compute the present value or the future value, not of a lump sum of a single amount. Suppose now that we have the same amount deposited or to be received at equidistant intervals. For example, we will receive 100 1 year from now, another 100 2 years from now, another 100 3 years from now. When we will receive or we will pay the same thing, the same amount, at the end of each year, during n years, we call this an annuity. And this annuity is an ordinary annuity when the different amounts to be paid or to be received occur at the end of each period, end of period 1, end of period 2, end of period 3, end of period n. Or when the first amount to be received or to be paid will occur 1 period from now. This is now the date 0. This is 1 period from now. We call it an ordinary annuity. Suppose now that the amounts to be paid or to be received will occur at the beginning of each period. So the first one will occur at the beginning of period 1. This is the beginning of period 1, the date 0, today. If the first amount will occur at the date 0, today, and we have n equal amounts for n years, we call it an annuity, and this annuity is an annuity due. So in timeline 1, the same deposit A is made at the end of each year for n years. We call it an ordinary annuity. In the timeline 2, we have the same deposits, but the timing of the deposit is not the same. The first one is deposited today. So all the deposits are made at the beginning of each period for n years, for n periods. This annuity is called an annuity due. Here, for example, when we have 3 annuities, when we take 3 equal deposits, if we start from 1, the last deposit will occur at the date 3, end of year 1, end of year 2, end of year 3. But if we start from the date 0, we still have 3 equal deposits. If the first one is deposited today, beginning of year 1, the second one will be deposited at the beginning of year 2, which is the date 1, and the last one at the beginning of year 3, which is the date 2. Now, how to compute the future value and the present value of a sequence of equal deposits made at equidistant intervals? Here we will take the case of the ordinary annuity separately, then we will take the case of an annuity due. You will notice that it is very simple. We will apply the same, well, the only formula we covered until now, which is future value n equal present value t times 1 plus I power n minus t. But this formula, which we applied until now for only one amount, we will apply it to the same amount that we will receive or what we will pay at the beginning of each year or at the end of each year. Then we will see what will be the formula. Can we determine a direct formula that will allow us to compute the future value or the present value of an annuity instead of computing the future value and the present value of each amount separately? So to save time, money, and to avoid errors in the calculation, we will try to, if you want, to determine a new formula from the previous one. So let's take the case of an ordinary annuity. As we said, an ordinary annuity, we have n A's deposited at the end of each year for n years. So we will start from the date 1. Since we have n years, n deposits, the last one will occur at the date n. Now, what will be the future value of this annuity, of all these A's? We will compound each A until the end of the date n. We will apply the formula we already know, for future value of a lump sum, to each A separately. So let's take the first A. First A deposited at the date 1 until the date n. What will be its future value at the date n? It would be A times 1 plus I power the number of periods of interest. From 1 to n, we have n minus 1, n minus t years. So it will be power n minus 1. Or for example here, from 1 to the date 3, what will be the future value of the first amount? It will be ordinary annuity times A times 1 plus I power 3 minus 1 years. 3 minus 1 times 2 years. We have from 1 to 3, 2 years of interest. So from 1 to n, we have n minus 1 years of interest. The same thing for the second A. The second A, from 2 to date n, we have n minus 2 years. The same thing for the date A of the date 3, date 4, etc. Now, A for the date n minus 1, this amount, its value at the date n will be A times 1 plus I power the difference between n and n minus 2. N minus, between parentheses, n minus 2. It will be on 1 plus I power 2. The 2 represents the 2 years of compounding. From n minus 2 to n, we have 2 years of interest. We have the power 2 here. The n minus 1 amount, A, is compounded for an additional year. From n minus 1 to n, we have n minus t, n minus, between parentheses, n minus 1, which give you the power 1. The last A will not generate any interest. because the power will be 1 plus I power n minus n. N minus tt is the same as n power 0. It will be remain the same. It will not generate any interest. So the future value of all these a's is simply the sum of what we got here. This represents, in mathematics, you saw this in the business calculus of the freshman level. This is the sum of the n first terms of a geometric progression. In a geometric progression, we have the first term, which is a. When we put a here outside the brackets, we will get this. The first term is a. This is a. And the random ratio is the amount that is repeated each year is 1 plus I. It is 1 plus I power 0 here, which is 1. 1 plus I power 1, 1 plus I power 2, until 1 plus I power n minus 1. From power 0 to power n minus 1, we have n terms. From 1 to n, we have n terms. And this sum of this geometric progression is equal to u1, the first term, times q, the random ratio power n minus 1, over q minus 1, or u1 times 1 minus q power n over 1 minus q, the same thing. Replacing u1 by a, q by 1 plus I, power n, you have the power n, minus 1, you have the minus 1, over the denominator, q minus 1, 1 plus I minus 1 will give you I. So directly, when we have an ordinary annuity, when we have a series of equal amounts deposited at equidistant intervals during n years, or we have n amounts, forget about the years, we have n deposits, n amounts. The future value of these n amounts at the date of the last deposit is very important, because when we have an ordinary annuity, the future value date coincides with the date of the last deposit. The last A occur at the date n if we start from 1. So at the date of the last deposit, we have future value of an annuity at the date n is equal to A, the constant amount, times 1 plus the interest rate power n minus 1 over I. Be careful here. This n in the power n that we have in this interest factor annuity, we call it in finance, this power n do not represent the date. In this particular case, it coincides with the date n, but this n in the formula of the future value or the present value of an annuity represents the number of A's. It's very important. N represents the number of A's. It's not the date n. Okay? So, for example, you can eliminate the first A or the second or both. So if you eliminate the first A, the number of A's will be n minus 1 A's. Just replace in this formula n by n minus 1, the number of A's. It's not the date. The future value date will not change. The future value date coincides with the date of the last deposit. So n here is not the date. N represents the number of A's. How many A's we have? If we subtract, for example, the first A, the formula will be power 1 plus I power n minus 1. If we subtract 1 and 2, both 1 and 2, the number of A's will be the sequence of A's deposited at equidistant intervals will be n minus 2 A's. It will be in the power n minus 2 in the formula. So be careful. The n in the formula of the annuity is not like the n in the formula of a lump sum here. The formula of the lump sum, N represents the number of years of interest. N in the formula of the annuity represents the number of deposits. I hope it is clear. Right. Now, let's take the case of the present value of the annuity. We will do the same thing. We will have somehow the future value of an annuity due now. The difference between an annuity due and an ordinary annuity, we said the first deposit is made today. So all the deposits will be made at the beginning of each year, not at the end of each year. If we still have N deposits, if we start from 0, the last one will be deposited at the date N-1. To get N deposits, if we start from 0, we finish at the date N-1. The future value date is still the date N. In this case of the annuity due, the future value date is 1 period after the date of the last deposit. 1 period after. Let's apply the basic formula we know. Future value of an ordinary of a lump sum to each deposit separately. A deposited at the date 0 worth at the date N. A times 1 plus I power the number of years of interest. And when we have a lump sum, a single amount, N represents the number of years of interest. From 0 to N, we have N minus 0, it will be power N. The second A occurring at the date 1, from 1 to N, we have N minus 1 period of interest, etc. The last one, from N minus 1 to N, we have 1 year of interest, or N minus, between parentheses, N minus 1 year of interest, power 1. We make the sum of all these future values. We make an arrangement. We note that A times 1 plus I is the first term, times 1 plus 1 plus I squared, 1 plus I, N minus 1. Like here, what we did here, when we have 1 plus 1 plus I squared until 1 plus I, N minus 1, this can be replaced by this term between brackets, which is the future value interest factor of an annuity. The same thing here. This can be replaced by 1 plus I power N minus 1 over I, the term between brackets. We have simply to multiply A times 1 plus I by this, which is the sum of the n first terms of a geometric progression. The first difference between this example and the previous one is that the first term is now A times 1 plus I. It's not A only. So we multiply A 1 plus I times the interest factor of an annuity. You will get the future value of an annuity due. Notice here that the future value of an annuity due is equal to the future value of an ordinary annuity covered in the previous slide times 1 plus I, So simply you have to memorize the previous formula only. When you have an annuity due, multiply it by 1 plus I. How to understand this 1 plus I? What is the source of this 1 plus I? This 1 plus I simply is due to this, because in this previous example, the last A will not generate any interest. In the annuity due, the last A will generate interest because the first one is invested one period before the A of the ordinary annuity, 1 year before the date of the first investment due when we use an ordinary annuity. This additional year of interest is captured by this 1 plus I. As simple as that. Let's apply it quickly. Compute the future value after 3 years of $100 payments occurring at the end of each period for 3 years. When we have 3 deposits with the same amount occurring at the end of each year, interest rate constant, 10%. Compute the future value at the date 3. This is an ordinary annuity because we know that each deposit is made at the end of each period. So it coincides with an ordinary annuity. Future value of an ordinary annuity is the A times 1 plus I power the number of A's. How many? 100. We have 3 amounts. So it will be power 3 minus 1 over I. You will get 331. Or if you have 3 deposits of 100 each. Suppose this ordinary annuity is 100, this one is 100, this one is 100. Since we have a limited number of deposits, we can compute the present value of each, the future value of each deposit separately. This 100 will be 100 times 1 plus 10% power 1 and 2. The second one will be 100 times 1 plus I power 1 from 2 to 3. And the last one will remain the same, 100. So the future value will be 100 times 1 plus I squared, 100 times 1 plus I power 1 plus 100. You will get the same result. Suppose now that the deposits are made at the beginning of each year, not at the end of each year. This coincides with an annuity due. The formula of the annuity due, as we said, is the same as the formula of the ordinary annuity, but we have to add the 1 plus I. So 1 plus I times the formula of the ordinary annuity. We still have 3 deposits. This is why the N reflects the number of A's, the number of 100. You'll get 364, or simply since the future value of an ordinary annuity is already computed here, 331, we multiply 331 by 1 plus I. You'll get the same thing. Or we can do the calculation like we did here. Each deposit separately, we have 3 deposits, we can do it. So the first A will be deposited for 3 years, from 0 to 1, from 1 to 2, and from 2 to 3, 3 years. So it will be power 3. The second one, 100 times 1 plus I power 2, from 1 to 3, we have 2 years. The last one, 100 times 1 plus I power 1, power 3 minus 2. You will get the calculations here, 364. And you notice here that the future value of an annuity due is higher than the future value of an ordinary annuity. It's logic. It is because of the additional year of interest, because we deposited the first amount earlier today, not 1 year from now. If we compute the present value of an ordinary annuity, the same logic. Instead of compounding the A's until the date N, we will discount the A's to the date 0. So the first A will be discounted for 1 year. From 1 to 0, we have 1 year of discounting, so power minus 1. The second A discounted will be discounted for 2 years, from 2 to 0, power minus 2, etc. The last one, from N to 0, it will be A times 1 plus I power minus N. We make this sum. We notice that we have a term that is repeated, 1A times 1 plus I power minus N. And between brackets, we still have the same sum, which can be replaced, as we said before, by 1 plus I power N minus 1 over I. We call this future value interest factor annuity. We multiply this by this term, A times 1 plus I power minus N. Then we make an arrangement. Since we have here 1 plus I power minus N times 1 plus I power N will give you 1 plus I power 0 minus N plus N. This is 1. By 1 plus I power 0 will give you 1. 1 plus I power minus N times minus 1 will give you minus 1 plus I power minus N. The denominator will be A. And you get directly a formula that will allow you to compute the present value of an ordinary annuity. Always N in the formula of the annuity refers to the number of A's, not the date. Not the date and not the number of years. This is a particular case here. When we have the first deposit made at the date 1, the second deposit at the date 2. This is why the date n coincides with the number of deposits. But in the real life, n will represent for sure the number of deposits, not the date. Okay? Well, not the number of years. It's the number of deposits. We can do the same thing for to do the same logic. Since the first deposit is made today, we don't need to discount it. Its value today is equal to a, not a times 1 plus I power minus 1, like in this case. So we will have an additional year of interest that we are saving. The last deposit here, a of the date n minus 1, its present value is a times 1 plus I power minus n minus 1. We have n minus 1 years of discounting. Not like here, we have n years of discounting. So here we will save 1 year of discounting. This additional, this year of discounting that we are not making, and we know that when we discount, we eliminate interest, we reduce the amount. Here the present value of an annuity due will be higher because the first amount and the last amount will occur earlier. We will not discount them too much. In the case of an ordinary annuity, we will have the same logic. Present value of an annuity due is equal to the present value of an ordinary annuity times 1 plus I, and this 1 plus I represents the difference between the present value of the last A for the ordinary annuity, which is A times 1 plus I power minus n, and the present value of the last A for an annuity due, which is only A times 1 plus I power minus n minus 1, not minus n. The number of years of discounting is lower here, so we will save interest here. This is why we have to add this 1 plus I in the formula, and you have the calculation here. So as we notice, the present value and the future value of an annuity due is equal to the present value or the future value of an ordinary annuity multiplied by 1 plus I. So always present value, future value of an annuity due is higher than the present value or the future value of an ordinary annuity. I hope it is clear. Let's take this example quickly. Compute the present value of $100 payments occurring at the end of each year for 3 years. If the interest rate is 10%. Here we have an annuity. Since the deposits are made at the end of each year, we compute the present value as 100 times 1 minus 1 plus I power minus 3 over I. The power here, 3, represents the number of A's, and in the formula of the present value, simply to facilitate the memorization of this formula, when you are asked to compute the future value, the n is positive. The power n is positive, 1 plus I power n before the minus 1. N is positive because we are adding interest. When we compound, when we pass from the present to the future, we add interest. So the power must be positive. But when we compute the present value, we are subtracting the interest. The power must be negative. It means that we will eliminate the interest. And 1 plus I power minus n is less than 1. This is why we put it after the 1, not 1 plus I power n minus n minus 1. It's not correct. So to facilitate things, remember this trick. Minus n to eliminate the interest discounting process, plus n, the positive power. When we add the interest, it means we are computing the future value of the annuity. Let's finish our example 9. Or if you forgot this formula, don't panic. Discount each amount separately. It will take more time for the calculation and it will increase the risk of errors in the calculation, but you can do it. Present value of the first A, value of the first 100, it will be 100 over 1 plus I power 1 plus 100 over 1 plus I power 2 years of discounting plus 100 over 1 plus I power 3 years of discounting. You will get the same present value, 248.69. If the deposits are made at the end of each year, at the beginning of each year, it is an annuity due. The difference between the two is this 1 plus I, additional 1 plus I in the formula. We still have 3 deposits. The power is 3, that reflects the number of deposits, and is negative to say that we are discounting, we are eliminating the interest. You get 273.55, which is 1 plus 10% times the present value of an ordinary annuity. Or you can discount each deposit separately. The first 100 will not be discounted because it occurs today. It will be 100 over 1 plus I power 0, no discounting. The second one, 100 over 1 plus I power 1 year of discounting. The third one, 100 over 1 plus I power 2 years of discounting. You will get the same present value. And notice here that the present value of an annuity due, like the future value of an annuity due, is higher than the present value of an ordinary annuity. Last thing to see here, Ejmia, is when the annuity has an unlimited life. It means that we will receive the same amount at the end of each year indefinitely. We call it the perpetuity. Suppose that we will receive the same A at the end of each year forever. What is the amount today that can replace these A's? Simply, this is the present value of an annuity. And specifically here, we have an annuity, since the first A will be received 1 year from now, and we want to compute its value today, 1 year before the date of the first amount to be received. This coincides with an ordinary annuity. Simply here, the number of A is the infinity, not N. The formula is the same, but the power here is minus the infinity, not minus N. Here, when the power is relatively high, for example, let's take even 100 years or 100 periods. 1 plus I power minus 100 will give you 0, approximately. So 1 plus I power minus the infinity will be 0. So the present value of an annuity, which is a perpetuity here, is A times 1 over I, which is A over I. So when we have a perpetuity, it means an ordinary annuity with an unlimited life. The present value of all the future amounts that we will receive indefinitely is equal to A, the first amount, or only one amount, divided by the discount rate. Let's take an example here. Suppose that we are asked to compute the present value of 100% at 10% of a 10-year $100 ordinary annuity. Means we need to compute, or we want to determine the value today of $100 that we will receive at the end of each year during 10 years if the discount rate is 10%. Simply, this is the present value of an ordinary annuity. N here represents the number of A's and number of 100. We have 10 100 and we need to discount them. This is why we put the power negative. Over I, we get 614.46. It means that we should be indifferent between receiving $100 at the end of each year during 10 years, or receiving today a single amount of $614.46 if the interest rate is 10%. So we should be indifferent between the two amounts. So 100 1 year from now, 100 2 years from now, until 100 10 years from now, can be replaced today by only one amount, which is 614.46. It's not 1,000. It's not 10 times 100. It's false. Okay? When we apply the principle of time value of money, the present value of 10 future amounts of $100, if the interest rate is 10% constant until the date 10, this amount, these 10 amounts can be replaced with a single amount of 614.46. Suppose now that we need to determine the amount that can replace 25-year ordinary annuity of $100 if the interest rate is 10%. Simply we will replace in this formula n by 25. And now we require $907.7 to replace 100, 100, 100 during the 25 next years. So what is the usefulness of this calculation? We will use this mainly in the next chapter when we invest, and we need to determine, for example, the maximum amount that we'll accept to pay today for an investment, knowing that this investment will generate for us at the end of each year 100, 100, 100 during 10 years. If we require each year a return of 10%, this will represent the required rate of return, 10% on this investment. What is the maximum amount we will accept to pay for this investment today, knowing that this investment will generate for us 100, 100, 100 during 10 years? If we want to gain each year 10% return. This will allow us to compute the maximum amount of investment that we will accept to pay today, which is equal to here to 614.46. So if in the real life the investment is equal to 614.46 or less than 614.46, we will accept to undertake this investment. But if it is higher than 614, it means that we will pay today higher than what we will get in the future. We will not accept the investment. This is the logic of the calculation that we will apply in the future chapters. Now, suppose that we have an annuity. It means that we will earn $100 forever. Suppose that we will invest today an amount, and this amount will generate for us indefinitely $100. What is the maximum investment that we will accept to pay today that will allow us to earn these 10% return that we require? Or simply in mathematics, what is the present value of 100, 100, 100, 100 that will occur forever if the discount rate is 10%? Simply, it's the present value of a perpetuity, which is equal to A over I, A over 10%, $1,000. It means that $100 that we expect to earn forever with the first 100 1 year from, will be received 1 year from now. If the interest rate is 10%, if our required rate of return is 10%, is equal to $1,000. We should be indifferent between receiving $1,000 today or receiving $100 at the end of each year forever if the interest rate is 10% annually. If we require from this investment 10% annually, we will accept to invest at maximum today $1,000 if the future earnings, the cash flows that we will receive in the future are 100, 104. I hope it is clear. We will stop here and we will continue this inshallah next week. Do you have questions?
Monsieur,
Yes.
أنا نحب نسألك على البارتي القديمة متاع وكل شيء. يا أخي ما فهمتش مسيو علاش أنت قلت الآن هي number of A's ماهيش